Hey everybody. I wanted to show you a way to do correlations in R that I think for a lot of you will make a lot more sense, and it's significantly easier or at least faster than using Excel to find the various pieces of the correlation. So I just wanted to go over that with you in case you'd like to use R completely for the exam as opposed to kind of splitting your time between Excel and R. So looking at some of the data we've seen before, where you have stress and ice cream, and you're trying to look at the correlation between stress and ice cream, you can see that there's four participants, and each of them has given a score on stress, a score on ice cream. They're both numeric variables, and so if we wanted to see the relationship between those, then a correlation is going to be the right kind of test. The way that you do a correlation, right, is you have to find deviations and multiply those deviations for each of these by each other, add those up, divide by n minus 1, and do all this other stuff to find covariance and then finally the correlation coefficient. And so that would look like this, right? Where you have made the deviations from the mean for, excuse me, for each of the participants for stress, deviations from the mean for each of the participants for ice cream. You multiply those things together. Find the covariance first, and then eventually, using the standard deviations, you can find a correlation. Okay, so it's kind of like a lot of work in Excel, but you can absolutely do that. And I've walked through that in class and online before, but now let's try to do the same thing in R, and you'll see how much faster it is. So we look at these in particular, the covariance is 1.5, and the correlation is 0.9045, or really if you round that up, it's going to be 0.91. So let's see if we can do something similar in R. Okay, so I've got the data in R, stress and ice cream, and what I'm going to do is simply type in COV. COV is the function for covariance, and put in some parentheses. Now I'm going to specify my first variable, which is going to be stress. You can do it in either order, it doesn't actually matter, but I'm going to do stress. So let's see, this data frame is called ice cream and stress. I'm going to specify with a $sign stress. I'm going to put in a comma and a space, and now I'm going to specify ice cream. So now we have covariance of stress and ice cream. I just hit enter and check that out. It's 1.5. It just tells you, right? Like you didn't have to go through all the work of doing deviations and multiplying them together and doing all that stuff in Excel. To find the correlation coefficient, which is also called Pearson's R, the function is COR. And I put in some parentheses. And again, I'm just going to put in exactly the same, oops, not that data frame, exactly the same variables of stress, comma, ice cream. Now we're doing the correlation coefficient for stress and ice cream. And check that out. It gives us a covariance of 1.5 and a correlation of 0.9045. Well, if you go back to the Excel file, that's the same thing. The covariance is 1.5, the correlation is 0.9045. And so you can do the same stuff in like a fraction of the time. Now, the thing is, right, when we do a correlation and we find the correlation coefficient, we still don't know if that correlation, which describes the strength and direction of the relationship between the two variables, this is a very strong positive correlation at 0.90. So that means that typically speaking, as stress increases, ice cream consumption also increases. You could think about it the other way. As ice cream tends to increase, ice cream consumption increases, stress tends to increase. In correlations, you don't know which way the variables cause each other or if they cause each other at all. So we just say, in general, as one of these increases, the other increases, and you know that because it's a positive correlation. Okay, but we don't know if this number right here is significant, is a statistically significant correlation coefficient. In order to figure that out, you would need to convert the correlation coefficient into an observed t-score. And then you would basically, with that observed t-score, and you convert R into a t-score using this equation, then you would compare the observed t, which is this, to a t critical, which you would find in the t table. depending on the degrees of freedom, which are n minus 2 for a correlation. Okay, well, you can do this by hand, no problem. And you can go through that as well. Or again, we can use our friend R and we can just do it in like a couple seconds. So to test whether a correlation is significant or not, there is a function called core.test, C-O-R dot test. And again, I'm going to put in parentheses and exactly the same thing. I'm just going to specify the first variable, comma, specify the second variable, which is ice cream, and hit enter. And now it's given us a test for the correlation. And you can see that the observed T, which is this one right here, it has already done that work for us. And the observed T is 3.0. The degrees of freedom, it says, are 2, and that's because there's 4 people in the sample. 4 minus 2 is 2. So n minus 2 is how you find degrees of freedom for correlations. And it tells you the p-value, which is 0.09. Now, on the exam, I would ask you something like you'd also have to look up the actual t-crit in the table, and so you'll want to know how to do that. But this p-value, since it's not significant because it's above 0.05, not significant because it's above 0.05, it already tells you that the t observed is not going to lie in the rejection region, meaning it's going to be not as extreme as the t critical. If this was significant of 0.05 or lower, then the T observed would be more extreme than the T critical and it would lie in the rejection region and therefore you reject the null. But in our case, it's not significant at above 0.05. So that therefore this T observed will not lie in the critical region and you fail to reject the null hypothesis. Okay. Oh, I should definitely point this out. This test in R is only for a two-tailed hypothesis test for correlations, okay? You can't change that. So it's only for a two-tailed hypothesis test. So on the exam, if I ask you for a one-tailed hypothesis test, you actually do have to go through and do the and you would find that the T observed and oh, actually, you can still use the same T observed. It's just that the T crit that you're comparing against is going to be for a one-tailed test. And so check this out. This is not significant. Let's actually go look at what the T crit is for a two-tailed test using this information here. So we know we have the degrees of freedom equal to 2, and we're going to use a two-tailed test. So let's actually go check that out. So degrees of freedom are 2, and a two-tailed test with the degrees or alpha of zero point zero 0.05. The T crit you can see is 4.303. That's the T crit. We went to 2 degrees of freedom and we went across to the 0.05 for a two-tailed test. So the T crit we're trying to reach is 4.303. Well, we didn't reach that because the T observed is only 3. So it's not more extreme than the T crit. And that's why this is a non-significant test and you would fail to reject the null. But if this was a one-tailed test, let's go back. Degrees of freedom equal to 2, and now we're talking about a one-tailed test with alpha is equal to 0.05. Well, now the T crit is only 2.92. Now the T crit is only 2.92. And if we go back to our degrees of freedom are 3. So 3 is more extreme than 2.92. Okay, so in that case, for a one-tailed test, it would be a significant correlation, and we would reject the null hypothesis that is not a significant relationship. So that goes to show you, you really only want to pay attention to this p-value if I've asked you about a two-tailed test. But for a one-tailed test, you're going to have to look up that T crit here in the table. Okay. Hopefully that was interesting and worthwhile. I definitely think doing all the stuff in correlations with correlations in R is going to be a better bet than walking through all the stuff in Excel just because it's less time consuming and there's less chance for making errors. But it's totally up to you. If you feel more comfortable using Excel for correlations, that's fine too. Okay, that's all for now. Have a good one.